So we're switching topics today, enough that we're switching books too. So for the next little while, I'm going to be following this book, Computing the Continuous Discretely, by Matt Beck and Sinai Robbins. So if you have it, great. If not, it's a nice book. It's very readable, and actually, I'm going to follow parts of the book, but you'll see that some of the proofs I'm going to do a little bit differently. So this will be kind of a nice complement to what I do in the class. Again, you don't need to buy the book, but you might find it helpful.
If you order from a school computer, you get it for $10.
So let me repeat that for the video. So if you order it from the school from a school computer, you get it for $10 digitally, presumably, or no, the whole thing.
You get the book.
Yeah.
But you can get it. Yeah, from that. Like somehow, remember, Mac told us he had to order from one of these guys that recognizes the computer and give us one of these textbooks that are on that program. We can get it from my office. You can actually get a PDF from that. Oh, really?
I won't repeat that on the microphone for his sake. So we're gonna spend at least a couple of weeks talking about the topic of counting lattice points in polytopes. You can think of this as basically measuring polytopes. But in a way, you're measuring them like a combinatorialist would measure them by counting. So you want to say how big a polytope is by counting something. So you can think of this as measuring polytopes discretely. Okay? But as I'll point out from the very title of the book, Computing the Continuous Discretely, you don't want to just think discretely. It's always good to go back and forth. Okay? And we'll do that. So let's say that you have a polytope in Rd. Okay? And what we're basically interested in is counting how many lattice points are in there. Okay? And so this means that we have a lattice, and we could do this over different lattices, but we're going to do it in the easiest way possible, which is that we're going to just take the lattice z to the d. Okay, so just all the points that have all their coordinates integer. Okay? And we want to compute how many points in P have all integer coordinates. Okay? That's basically the topic of the next little while. Okay? So in fact, I'm going to be a little bit more ambitious, and I want to count the lattice points not only in P, but in all the scaled versions of P, where I take P and I dilate it by some factor of T. Where T is some natural number. Okay? And this I'm going to call this function. Of course, it depends on T. It depends on the scaling factor. And so I'm going to call it L sub P of T. Okay? Now, another thing that we're going to be interested in is computing the lattice points that are in the interior of P. Okay? So the boundary doesn't count, but just the interior. So let's denote that by P with a little circle here. So this is going to be the relative interior of P. And then we can also just decide to count how many lattice points are in the interior, or we can scale it by a factor of T. Okay, and I'm going to call this L sub P interior of T. Okay. And let me introduce the last bit of notation, which is I'm going to define just like we had last time a generating function for Catalan numbers, here we're going to do a generating function for these things. Okay, so what I'm going to do is just count this for each value of t and then make a series out of it. Okay, so I'm going to consider the infinite series from t equals 0 to infinity of this thing and then z to the t. Okay. This is the generating function, and it's known as the Ehrhart series. Okay. So this is just these are some of the main characters that we're going to be working with for the next little while. And what I wanted to do today is just compute some examples of this so that you get a good idea of what these things are, and you get a better intuition for what we're doing here. Okay. So I want to do a couple of examples. So first example is the cube. Okay. And now I'm going to denote it differently. I'm going to denote it by a little square because I want to move it. So remember that the cube that we considered was between -1 and 1, and that was convenient because we were doing polarity there. But here it turns out to be, I mean, it's not a big deal, but it's a little bit more convenient if we consider the cube between 0 and 1. Okay. In some sense, I would say that this version of the cube is even more natural than the one we were considering so far. Okay. So this is going to be P, the d-dimensional cube, and let's compute these things. Okay. So what is TP? Well, it's scaling this thing by t in every direction, right? So, I mean, one way of saying it is that, I mean, maybe I can say that these are the x's in r to the d, such that each xi is between 0 and 1 for all I between 1 and d. Okay, and so naturally, if I scale my polytope by a factor of t, then basically in the inequality description everything gets scaled by t. Okay? Well, the right hand side gets scaled by t. So if you take a number between 0 and 1 and you scale it by t, then it becomes a number between 0 and t. Right? So what we have here now is the points in Rd, which have coordinates between 0 and t. Okay. So that's Tp. And then if we consider the interior of that, what we're doing is that we are looking at the points that satisfy these inequalities, but they should not satisfy any equalities. Okay, because if you satisfy an equality, that means that you're on a facet. And so basically, we just take the same thing. We just make our inequalities strict. Okay. So those are TP and TP interior. Okay. Now what I'm interested in the lattice points in here. So let me intersect this with z to the d. And what that's going to do is basically that instead of considering the x's in r to the d, I'm just going to consider x's in z to the d. Okay, so if I intersect this with z to the d, then, so is everybody looking? Because I'm erasing. I actually always hate it when people erase what I already took down on my notes. But anyway, so I intersect with z to the d, so then instead of considering x to be in r to the d, I consider it in z to the d. And I'm going to do the same with this one, okay? Okay. So so these are my sets, and now what I want to do is compute. So what is L sub d-dimensional cube of t? Okay, how many points do I have in here? What do you guys think? So basically, it's t plus 1 to the d, and the reason is the following, that you get to choose each coordinate independently, right? The inequalities talk about individual coordinates. And what you get to do is that you get to choose each coordinate to be any number between 0 and t, but it has to be an integer. Okay, so it has to be 0, 1, 2, or all the way up to t. And between 0 and t, we have t plus 1 numbers. Okay? So we have to choose d coordinates. For each one, I have t plus 1 options. And so the number of ways is t plus 1 times t plus 1, and so on. T plus 1 to the d, because I have t plus 1 choices for each coordinate.
I guess I was thinking about it as the line from 0 to t has t plus 1 integer points in it, and then I just dilate it.
Mm-hmm. And that's basically the same thing that I'm saying, but I'm saying it maybe a little bit more combinatorially. You're saying it a little bit more geometrically. So that's L. Okay. Now what's L interior? Can you say it more loudly, Dito? T minus 1 to the d. And why is that? Because we have almost the same choices, but now you're not allowed to choose coordinates equal to 0 or to t. So for each coordinate, now you only have the choices 1, 2, up to t minus 1. So t minus 1 choices for each coordinate. Okay? You know what? Instead of saying L this, L that, let me actually tell you what the names of these things are, because actually I think maybe some of you know already. This function that I wrote here is called the Ehrhart polynomial of P. Okay, and this you can maybe call the interior Ehrhart polynomial, and this one here is called the Ehrhart series of P. Okay, now why hadn't I told you the name yet? Because there's a bit of a, I mean, what you see what I'm saying is more than a definition, because I'm calling it a polynomial. And the way that I define it, you cannot at all tell that it's a polynomial, right? I'm just saying count something, it's a function of t, and all of a sudden I call it a polynomial. At least in this case, it's true that it is a polynomial in t, okay? And maybe what I'll do is put a little red square around this so that you realize that so far we don't know that it's a polynomial, but it's, of course, if it's called this, then it's because it is a polynomial, right? And we will prove that it's a polynomial, but we don't know that yet. Okay? So for now, let me put a little question mark, because it's not clear that it's a polynomial, but here you see that it is a polynomial. Okay? Okay, now let's put a little box about around these things, and let me make an observation that is so. What is the Ehrhart polynomial of minus t? Well, it's not clear what that should mean here. Maybe it should mean that I should scale by minus t, meaning that I kind of scale by t and then invert the polytope. What I'm going to do basically is just take this function and just plug in minus t and see what I get. Okay. So what do I get? Plug in minus t, so I get minus t plus 1 to the d. Okay. And if I take out a factor of minus 1 to the d, I get t minus 1 to the d, which is this one. Okay. So here's kind of an interesting equation, and I think it's kind of a counterintuitive equation because I mean, if you think about what I said, what would it mean to plug in minus t? It would mean to consider the polytope minus tp, which you would think would just be the polytope tp, but with a minus sign, so it's just a reflection of that. And if you count the lattice points on that, it's just the same thing as tp. Okay, but somehow that's not what happens. So if you plug in minus t, then you do get to count points in your original polytope, but somehow you forget the points on the boundary. Okay, and you just consider the interior points. And that's something kind of strange, but it's true. You're seeing it before your eyes. Right? And of course, the point is that this formula is only true for t, a natural number. And so it's completely, I mean, if I plug in minus 3, then I have no right to expect anything of that because this formula only holds for positive numbers. Okay? And so this is just some kind of strange observation that if you plug in minus t, you get something. And this is what you get. Okay? Okay, let's compute this Ehrhart series now. So the Ehrhart series as a function of z, summation from t equals 0 to infinity of the Ehrhart polynomial, which is t plus 1 to the d, and then z to the t. Okay? That's the Ehrhart series. Now, do you guys know how to compute this? Do you recognize it? Have you seen it before? I mean, it's kind of a nice series. It wouldn't be too out of place in an analysis class, as you know, here's a series computed. But I don't think that you saw that in your analysis class. Let's compute some values, and then maybe we'll see what happens. Okay. So for d equals 0, what are we saying? So the Ehrhart polynomial of. So when d equals 0, I just get sum from t equals 0 to infinity. T plus 1 to the 0 is 1. Z to the t. Okay. So you guys know how to compute this one, right? That's the geometric series, and that is 1 over 1 minus z. Okay. And again, here you have two choices. You can choose to be a stubborn algebraist and do this over the field of formal power series, and it works. Or you can choose to accept that it's okay to mix algebra, combinatorics, analysis in the same place, and then you can say, well, this converges for z of absolute value less than 1, and then this is really an identity of meromorphic functions. Okay, but that's not very instructive. I mean, that's only the first one. So what about the next one? Sum from t equals 0 to infinity of t plus 1 to the 1, z to the t. So do you guys have any idea how I could compute this one? This is a derivative, right? This is very clearly a derivative. So we should not fight our temptation to recognize it as a derivative. This is the derivative of z to the t plus 1. Okay? And so that means that if I change the order of the sum and the derivative, I get this. Okay? And what is this sum right here? Well, this is z plus z squared plus z cubed, etc. So it's our previous sum, except that is missing the first term, right? So it's the derivative of this. Okay? And what's the derivative of this? It's this is 1 minus z to the minus 1, so you get 1 minus z to the minus 2. So you get 1 over 1 minus z squared. Okay, so that's another nice nice answer. Okay. It depends who you ask. So if I'm a stubborn algebraist, I'm going to tell you that z is the argument in my ring of formal power series. So maybe I'm doing the computations over the ring of formal power series in z. But I could also tell you z is some complex number of norm less than 1, and then this is analysis. Okay. And I mean it. Both work. Okay. Okay. Nice answer. How about the next one? D equals 2. Actually, the Colombian students complain that I write too small, so I'm going to write bigger. I don't think it's true that I write too small, but I guess the camera doesn't have a lot of range. Or their screens are too small, maybe. Anyway. D equals 2. So Ehrhart polynomial of Ehrhart series of squared 2. So this is the summation from t equals 0 to infinity of t plus 1 squared z to the t. Okay? And now I'll take your suggestions. How can I compute this? By the way, let me say something that I didn't say, which is that you might complain that in the ring of formal power series there are no derivatives. Because you know, rings, we think of rings as having a sum, a product, but not a derivative. But I will tell you that there is also an algebraic machinery. There is an algebraic way of doing derivatives in this ring. And that's where I'm saying it really takes some stubbornness to say, no, I really don't want to think of z as a complex number. And it works. And there are ways of saying, well, you know, what's the derivative of a series? Well, you just take the formal derivative of each term. Okay? You can make that work. Okay. So what about this one? How do I compute this? So let's pull out a t plus 1. And then this is the derivative of z to the t plus 1. Right? And again, let me switch the order. So then I get the derivative of t plus 1, z to the t plus 1. And now what is this? How do I compute this? It's basically z times this one, right? It's exactly z times this one. So that's z over 1 minus z squared. Okay? And then you have to do this, okay? You take the derivative, and what you're going to get is this. 1 plus z over 1 minus z cubed. Okay? We keep getting these nice formulas. We're getting nice answers. Do you believe that you could keep doing this? Personally, could you do it? If I asked you to compute the next one? You could do the same thing. Stick out the t plus 1, factor. You can repeat this argument and you can compute the next one and the next one and the next one. Let me tell you what you get if you do that. So the next one is 1 plus 4z plus z squared over 1 minus z to the fourth. And the next one is 1 plus 11z plus 11z squared plus z cubed over 1 minus z to the fifth. Okay? And I could compute more if I wanted to. But I think you'll agree that these are nice answers. These are I mean, you certainly see some patterns emerging, right? And so, I mean, this calls for a theorem. You can already begin to write a theorem, and hopefully you can prove it too. So let's write a theorem. Tell me what I should put in this theorem. Tell me something about the answer. The denominator is something very nice and predictable. 1 minus z to the d plus 1 power. By saying you have coefficients, you're implicitly telling me that the numerator is a polynomial. Right? And so, let's I have a typo here, but it's fine. The numerator is a polynomial of degree d minus 1, right? We agree. And so let me just I'm going to give names to the coefficients. And there's a reason why I give them those names, okay? So those coefficients look familiar to you. I mean, one thing, let me tell you what combinatorialists. Combinatorialists are very happy when they see positive numbers, because then they say, oh, that means that I'm counting something, right? And so here we see that the numerator has all positive coefficients. They're all positive integers. And the immediate question in a combinatorialist head is, what does that count?
Well, it's also palindromic, right?
It's also palindromic.
Well, so far.
So far. And a combinatorialist is asking, what does this 11 mean? It must be counting something because it's a positive integer, right? So it's an answer to a counting problem. That's the way that we think. It turns out that the answer is very beautiful. I mean, look at something. What happens when you add up the coefficients of the numerator? Here, let's start less ambitious. So we add up the coefficients of the numerator. Here we get 1. Here we get 1. Here we get 2. Here we get 6. Here we get 24. So what sequence starts 1, 1, 2, 6, 24? In factorial. 1, 1, 2, 6, 24. That's 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. So that must mean we're counting permutations because they're factorials, right? It turns out that it's true. So where a of d comma k is the number of permutations of the numbers from 1 up to d, such that and let me first tell you in words what I want to say that they are permutations with k descents. And what I mean by this is that a permutation is an ordering of the numbers from 1 up to d, and you're just going to count how many times the permutation went down. How many times is a number bigger than the number next to it. Okay. So if I call it my permutation pi, then a descent is a number I such that pi of I is bigger than pi of I plus 1. Okay? And this is the theorem. Okay? So let's, just to make sure that we're clear, let's do this for d equals 3. Let's list all the permutations and the number of descents. Okay, so the permutations of 1 up to 3 are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Okay? And a descent is a place where the permutation goes down. So you see this first permutation never goes down. This one goes down between 3 and 2. This one goes down between 2 and 1. This one goes down between 3 and 1. This one goes down between 3 and 1. And this one goes down here and here. That means that this has 0 descents. These have 1 descent. And this one has 2 descents. Okay? And that is telling me that the numerator of the third Ehrhart series should be 1 plus 4z plus z squared, which it is. Okay? So is it clear at least what the statement is saying? And now you see why this doesn't really belong in an analysis class either. I mean, it's really a very explicit series, and the answer turns out to be very combinatorial. This is one of these places where you're really beginning to see the things come together. Okay? Sorry, k plus 1 descents. You mean that here? No. Okay. This is k minus 1, I'm sorry. Any other questions about this proposition? So I wanted to show you this as a first idea of what are the kinds of results that we obtain here and that we like. Okay, so this is a nice example of a very explicit formula, and
What are those numbers called?
These are called Eulerian numbers. Yeah. And they're called Eulerian numbers because Euler was able to compute these series, basically. So Euler was the first one to compute those series explicitly. Although I don't think he actually figured out that this was what those numbers were counting. But he was the first one to consider that series. Okay? Okay. Any questions about this?
Yeah. This talking about the number of permutations. Okay, so we can match these things up, but what's the connection to the different permutations? I mean, is there
So are you asking why on earth this is true? Is that your question?
No,
I mean, you should be asking that. But okay, so what's
geometrically, is there a reason for this? I guess it's the same thing as asking why the hell is it true.
Yeah. So by the way, you're gonna hate the answer.
I wonder if it's just because it lines up, but
No, the answer is that it's in your homework. No, actually, that's an exciting answer because I think you really get to figure it out. But I'm gonna basically break it down into steps that are very reasonable. Okay. By basically this is not too hard to prove by induction, basically. But there are better ways of explaining this, more geometric. And we'll see if I get to that. But
that's what I was asking. I mean, I fully believe that we can prove this is true. That doesn't tell us why it's true.
Yeah.
I mean, what geometric argument are we making here, or are we counting something here? I mean, when I see the permutations, I think that we're counting something.
Yeah. So there's a very nice explanation of this identity coming from something called the theory of p partitions. Which I don't think that we're going to do in this class. It's part of Stanley's big book in enumerative combinatorics. If you or anybody else is interested in thinking about this more for the project, that's a good topic. But unfortunately, I don't think that I will get to give you a nice, clean explanation because it's just not so simple. The answer is just not so simple, I think. So I wanted to discuss a second example. I mean, we already discussed the cube, and so the natural next example is the simplex, but a very special simplex. Since the simplex, we already saw it. Remember that if it's d-dimensional, then it lives in d+1 dimensions. All the xi's are greater than or equal to 0, and they add up to 1. Okay? So let's talk about P interior. Okay? Because this is going to be a little bit easier to compute. So these are the x's in R to the d+1 such that xi is bigger than 0 and x1 up to xd. Now, these used to add up to 1, but now I scaled by t, so they're going to add up to t. Right? So these are the things that we're counting. Okay? Now let me intersect with lattice points because that's what I want to do. So when I intersect this with the lattice, then I'm looking for integer solutions to this. Okay. They sum up to t because if you think about it. For example, this is delta 2, right? X plus y plus z equals 1, and x, y, and z bigger than or equal to 0. And that means that x plus y plus z is equal to 1 in this whole plane. And the inequalities really come from these restrictions, okay? And so that's where I should change to strict inequalities, but the sum is the same. Okay. Now, the next thing that I want to do is I want to say, okay, well, if I'm looking for integers, then an integer bigger than 0 is an integer bigger than or equal to 1. Do you agree? So instead of saying bigger than 0, I'm going to say greater than or equal to 1. And so what I'm doing is that I am looking for the number of ways. Well, this is supposed to be d plus 1, right? Because I have d plus 1 variables. So I'm looking for the number of ways to write the number t as a sum of d plus 1 integers. Does that look familiar to you guys? Have you done that? Maybe some of you have if you've taken a combinatorics class. There's a nice trick to do this. So, well, let me spell it out. Number of ways to write d plus 1 as, to write t as a sum of d plus 1 positive integers. And there's a nice trick to count this, which is to say, well, let me take d plus 1 once. Okay. And let me insert t minus 1 plus signs in here. Okay. I inserted t minus 1 plus signs. When I do that, I have a way of writing d plus 1 as, no, I'm trying to write t, sorry. So what I want is to have t once. Okay. And then I want to have d plus signs. Okay. So when I do this, in this case, t is 1, 2, 3, 4, 5, 6, 7, 8, 9. What I get is a way of writing 9 as a sum of 3 plus 3 plus 1 plus 2. Okay? Which is one of the ways of doing this. Okay? And if I have d plus signs, then I have d plus 1 summands. And this is a bijection. Okay? This precisely describes the ways of doing this. And that means that the number of ways to do this is basically, you see, I have t1s, which means that I have t minus 1 slots where I can put my plus signs, and out of those t minus 1 slots, I need to choose d. Okay? And so this is what I get. And this is L sub p 0 of t. Okay? Now what's LP of t? Now what I need is the number of ways to write t as a sum of d plus 1. The difference now is that now I'm not in the interior. Now I'm looking for points anywhere in the polytope, which means that instead of xi bigger than or equal to 1, I have my original inequality xi greater than or equal to 0. So I'm looking for ways of writing t as a sum of d plus 1 non-negative integers. And again, here there's a nice trick, which is to say that if I wrote t as a sum of d plus 1 non-negative integers, now take each one of those integers and add 1 to it. Okay, so if t is equal to a0 plus, a1 plus dot 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 plus ad plus 1, where these guys are bigger than or equal to 0, then I'm going to add 1 to each one of these things, each one of these terms. Okay, and now they are greater than or equal to 1. And what do they add up to? Well, it was t, but now I added d plus 1 once. So t plus d plus 1. So this is the number of ways to write t plus d plus 1, because this is a bijection, as a sum of d plus 1 positive integers. So I reduce it to the previous computation, and what I get is, make sure I get this right, t plus d plus 1 minus 1, choose d, or t plus d, choose d. Okay. So again, here I get very nice explicit formulas. Now, maybe I'll write the other one here. Now remember that in the first example that I did this strange thing, which was to plug in minus t instead of t. And I tried to see what happened. If I do that here, I'm going to get minus t plus d, choose d. Okay? And now, what is this? Well, it's minus t plus d, minus t plus d minus 1, minus t plus d minus 2, dot, 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 up to minus t plus d minus d minus 1 over d factorial. Okay. Now, I'm going to pull out a minus sign out of each one of these things. I have d terms. So I get minus 1 to the d, and I'm going to change the sign of everything. So you see here, I get t minus d. Here I get t plus 1 minus d. Here I get t plus 2 minus d. Dot, dot, dot. And then what do I get here? This is minus t plus d minus d plus 1. So I get t minus 1. And then, if you look at what this is t minus 1, t minus 2, dot, 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 up until t minus d over d factorial, which is precisely t minus 1 choose d. Okay? So the same phenomenon holds true here, that what I get is the interior point count. So that's a very nice phenomenon that we saw in the previous case, also holds true here. And well, as you can imagine, my point is that it always holds for any polytope. Finally, let me just state what happens when you do the Ehrhart series. What you're going to get is the summation for d greater than or equal to 0 of t plus d, choose d, z to the d. Now, it turns out, you see here, I did this computation where I took a binomial coefficient and I turned it into a different one with a sign. I can do the same trick here and get minus 1 to the d, and then I get minus d plus 1 choose t. Z to the t, thank you. Yeah. And this is also t. Summation over t. Yeah. And so you see what I get here is summation for t greater than or equal to 0 minus d plus 1 choose t, and then minus z to the t. And if you look at what this series is, this is just a straight binomial theorem, right? It's 1 minus z to the minus d plus 1. So in other words, the Ehrhart series of this thing is beautiful. It's just this. Okay. And so again, it's a polynomial divided by 1 minus z over d to the d plus 1. And it just so happens that this polynomial is the simplest that it could possibly be. Now all of this depends on this computation, which I skipped. And that, I think, is a nice exercise for you to do, to see that these two things are equal to each other. But yeah, so I hope this gives you a feeling for what is to come next. And what we want to do now is do this not just for the cube or the simplex, but for any polytope. That's our next goal. Okay. So I think I'll stop there.